Okay, this is chapter 2. And chapter 2 deals with kinematics in one dimension. So now we're talking about the motion of an object in one direction. And so when I say one direction, that can mean in a vertical direction or a horizontal direction or some combination of both. Okay. But uh, in one direction. Okay. And so the contents of chapter 2 are as follows. We'll talk about reference frames briefly, reference frames and displacement. We'll talk briefly about velocity, average velocity, and instantaneous velocity. Also talk about acceleration and what acceleration actually is. Right? We also talk about motion at a constant acceleration. All right, motion at a constant acceleration, which is a very important principle in physics. Okay, and particularly in kinematics. Okay, and we'll solve some problems like we always do, and we'll talk briefly about, or we'll go over some problem solving strategies. Okay, and we'll then move into free fall, and then we'll do some graphical analysis. Oh, excuse me. All right, so reference frames. So any measurement of position, distance, or speed must be made with respect to a reference frame, right? So if you pay attention to the cartoon at the bottom of the image of the screen here, you'll see that you have 3 individuals on a train. 2 of them are in a sitting position, right? So they actually move in the same reference frame with the train, okay? The third individual, the standing individual, is moving on the train. So that individual has 2 sets of motion, right? Of course, the person is on the train, so it's moving in the reference frame of the train, right? But it also has a motion associated with its movement on the train, if that makes any sense. So if you're on this, if I'm standing on the ground, right, with respect to Earth, when I stand on the ground, my reference frame is Earth, the planet Earth. That's what my reference frame is. And so when I stand on the ground and I watch that train pass by me with those 3 individuals on it, the 2 individuals sitting down are going to appear to move at a different rate than the person standing. All right? Even though all 3 are on the same train. Well, 2 of them are sitting, obviously, right? But those 2, right, they'll appear to be moving differently. Why? Because, uh, again, I'm standing on the ground with respect. So my reference frame is with respect to the Earth. Okay, and so the reference frame uh, of the 2 individuals sitting down is with respect to the train. Okay, and the individual sitting or walking on the train has his motion can be described with respect to the train plus there are his own reference frame, right? Because he has his own motion on the train. Okay. So that leads us to a discussion between what's the difference between distance and displacement. Okay. Displacement is how far the object is from its starting point, regardless of how it got there. Okay? And distance is the actual length or the actual measured path, right, that you travel. Okay? All right? In other words, right, so if I have a track meet or a track person, they begin and end at, so if they're running I think it's the 400 meters. That's one time around the track. I think that's it. They begin and end in the same spot. So the question is, well, what was the person's velocity and what was the person's speed? Right? How fast did they move around the track? Okay, because they started from one point and they ended up in the same point. Okay, but we know they went somewhere. We know that they didn't not go anywhere, right? So the difference there is the person's displacement is 0, right? Because they ended up in the same spot that they started from, right? The distance is not 0, obviously, because they had to cover some distance to get around the track. So that's the difference between displacement and distance, okay? But we're going to dig deeper into that when we start talking about velocity, all right? Oh, let me go back, and I just want to point out that this little figure at the bottom here, and we see the blue arrow, which is pointing in the east or the eastern direction, right? Ultimately, right? But we started out, right? If you pay attention to the dash line, then it says what? We started out, we went 70 meters east, and then we went back what? 30 meters in the west direction, okay? Which ultimately lands us with a displacement, right? Because it's the difference between the starting position and the ending position, right? So the starting position here was what? 0, and the ending position was 40, even though we went 70 meters and then we came back 30. So that's the difference between distance and displacement. And so here's a definition. It's a mathematical definition, right? And the delta sign, delta x is the difference between position 1 and position 2, right? And so if you pay attention to the cartoons, then on the left-hand side, we see what? Displacement is positive. So we started at 10 meters and we ended at 30 meters. So that'd be what? 30 minus 10. So we have a displacement of 20. So on the right, we have displacement, which is negative, right? Because why? Because we started at 30 and we ended at 10. So that would be what? 10 minus 30, giving us a negative 20. Okay? So that basically explains, right, the difference between distance and displacement, which leads us to the difference between speed or average speed and average velocity. Okay? So speed is one thing. That's what we're accustomed to saying, right? But in physics, we talk about velocities. And why is it that we talk about velocity as opposed to speed, right? It's because velocity takes into account the direction, okay, which is very important. And you're going to see, particularly when we get to chapters 4 and 5 and so on and so forth, you're going to see why it's very important to indicate what direction something is acting, in which direction, right? See, right now, the only direction that we haven't talked about any forces yet, right? But we are introducing gravity. Okay, maybe not, maybe not so much right now, but we're leading up to gravity. Okay, and gravity is a force or an acceleration. I shouldn't say that it's an acceleration which causes a force that acts in the direction towards the earth. Okay? And so gravity doesn't make sense in any other direction, only towards the earth. Okay? So that's one example. And so this is a plot of uh, an object in motion, right? And to the left hand side, we see that the motion of that object, so that's a constant, that's a horizontal, constant line, right? And I know it's constant because it's flat. It's a flat line and it's horizontal. So that means it's constantly traveling at what? 40 kilometers per hour. Time is on the x-axis, velocity is on the y-axis. Okay, so if I look at the plot to the right, then I notice that what? That object, it starts from 0, right? Speeds up to about what? 50 kilometers per hour, stays there for a little while, right? Then decides to what? Slow down to about 20. Then stays at 20 for a while and then eventually just stops. Okay? So we see that there's a change in motion there. That's not a constant motion. So then that means there's some acceleration, right? Acceleration, whether that's speeding up or slowing down, right? That is an acceleration or a deceleration. Okay? And so acceleration is the rate of change of the velocity. So how fast you speed up. That's how that's how that's how much you accelerate. How fast you speed up, right? Or how fast you slow down. That's deceleration. Okay? So, we have to remember that acceleration is a change of velocity, meaning the velocity either it changed, okay? And when we introduce direction, you're going to see that when you change direction, that's also changing the velocity, right? Might not be changing the speed, but you're changing the velocity. So these things we have to be very careful about in physics. There are two different things. One is speed, one is velocity. Velocity and speed and velocity can be the same thing, but they are not. Oftentimes they are the same thing, but they are not the same thing. Okay? And again, acceleration is a vector. So that's what we're leading up to, vectors. So we're going to talk about vectors in chapter 3. We're going to talk about them extensively in chapter 3. And we're going to do a lot of vector math, right? So we're going to go back to the trigonometry and all of that stuff we did in high school and Pythagorean theorem and all of that stuff. Okay. So this is just an image of a car slowing down, right? So it started at what? 15 meters per second, and then it ended up at 5 meters per second. So that means it slowed down. Okay, it decelerated, or it had a negative acceleration. Okay. All right. And so yeah, so this is just this is another tricky thing in physics where, you can easily make a mistake and believe that uh, one thing is occurring, but it's not. It's just it's just the fact that you're moving in a different direction now, right? Like it's like when you think about the number line, and you think about uh, you know traditionally you're taught that the further you are away from zero, right, on a number line going right, you're gonna get larger, right? But the opposite is true going left, right? Further I go left, right, on the number line from zero, I'm getting smaller. But the actual number might be, or the actual magnitude of the number might be getting bigger. But it's in actuality, you're getting smaller because you're going further away from zero in the negative direction, if that makes sense to you. Okay? So acceleration, and I didn't mention it, but acceleration is I know and we could just go really back really quick, right? So this is the limit. I didn't mention it, but because we're in a algebra based class, this is calculus, so we're not going to be talking about any derivatives, but it's the same thing, right? That in order to calculate the velocity of an object, we could do the first derivative of the position vector. Okay? And the same is true, we can do the first derivative of the velocity vector with respect to time and get acceleration. Or we can do the second derivative, the second derivative of the position vector, right, to get acceleration. Okay? So, but that's all calculus. Don't worry about that. All right. So, average velocity of an object during a time interval, right? So, when you see a bar over something like that, that's the average. That's the average velocity. That's like taking, if you got three things, you add them up, then you divide by three, you're gonna get the average. Same deal with four things. You add them all up, then you divide by four, you get the average. Okay, so average velocity is one thing, right? And that's what we're gonna be dealing with algebra based physics. So that's why they introduced the derivative, because the derivative allows you to uh, calculate certain things with a little more accuracy than an average, right? So when you talk about algebra based physics, we're talking about averages and stuff like that, which is good, which is good enough. Okay, we don't have to be we don't have to have a 95% confidence interval. Okay, we don't have to have that degree of precision and accuracy. All right, it's not necessary. But anyway, same way we calculate the average velocity, we can do uh, or we calculate the average velocity, and then we can calculate the acceleration, right? And you see those two equations right there. All right, and you see the bar over the v, and then we see delta x. Delta stands for difference, right? X2 minus x1, or x minus x naught. The zero, the subscript zero, that's what I'm calling as naught. That's x naught. X minus x naught over t minus t naught. Okay? So we can calculate average velocity, and then we can get an acceleration, and so on, so on and so forth. So you see how a lot of these things are related to each other. So if we do some basic algebra and and rearrange some equations and do all of that. Then we arrive at this, and I don't know what's going on with that. There we go. Oh, well, maybe it's going to come back. Well, let me do this. Let's raise it up a little bit. Will it work? Will that work? Or will I go to the next slide? Well, I can't move the mouse. Or, well, if I can, then I don't know how. Sorry. So the last equation on the bottom of the screen says x equals x naught plus v naught t plus 1/2 at squared, right? So that is the constant acceleration. So we see that at the top, right? Motion at constant acceleration. So this is the equation. This is going to be a very important equation for you. Okay, you need to write this one down, commit it to memory, understand what every letter represents in the equation. That's how you do this. Okay, you need to understand which each term in the equation represents. And I mean the words. Like x is position. Like how far. Like if I'm calculating how far, I'm calculating the x, distance. V naught is the initial speed. What speed or initial velocity? What velocity did I start off at? Because sometimes things start off at one velocity and end up at another velocity. So we will have two velocities. All right? So this says the initial velocity. Okay? And A stands for acceleration, right? And then when we talk about in the y direction, right? Because this is in the x direction, right? X is the horizontal. But if we're talking about the vertical, which is the y, then that A turns into G, which is gravity, right? So gravity is what accelerates things in the vertical direction towards the earth. And obviously T is for time. All right. So these are some pretty important equations here. So I just want to point your attention. That's at the bottom left, in the bottom left-hand corner, that's the one we just went over. That's the constant acceleration equation. That's very valuable. Actually, we're going to be using that quite a bit in chapter 4 when we start talking about projectile motions and we start talking about how things like a missile or a football or any kind of projectile, a javelin, right? Anything that you throw, okay? But when we start talking about that equation is going to be very useful. And so that equation 2-11b is very useful. And 2-11c, that's called the golden rule. And the reason why that equation is useful is because it contains acceleration, A, right? And you're going to understand why I say that, right? And it contains the initial and the final speeds, right? Which is a lot of times when you start to read these problems, and there are going to be certain things that they give you, and you're gonna be like, oh, I know which equation. It's obvious, right? Because there are certain equations you have to have certain things in order to solve them correctly. Okay, but pay attention to 2-11b and 2-11c. All right, so solving problems. So basically, it's just like going back to our high school days where we were even middle school, right? Where we started doing the word problems, and We had a little strategy that we used for that. Okay. And so that's what this is. This is going to be our strategy. So we're going to get plenty of practice with this. I'm not going to read these to you. We're going to get plenty of practice with this as we practice these problems over the next week. And yeah, and we're going to put this into practice. Okay. Yep. 1 through 9. All right, so let's move on to free falling objects, right? So free falling objects are obviously things that are falling towards to the earth, right? And like I said, this is one of the most common examples of motion with constant acceleration. So that equation that we were just talking about, I think that's what 2-11b. That equation, that's the one they're talking about. So this image here relates to that equation. Okay. So why is it what's so special about free fall objects, right? Is because it's the who wants to be a millionaire question, right? So I have a bowling ball in one hand and I have a marble in the other hand. I drop both of them at the same time. Which one hits the ground first? Most people will say, "Oh, that's easy. The bowling ball," right? Because the bowling ball is heavier, it's bigger, blah blah blah, right? But that's not the case, right? Because the earth is so big, right? Compared to the bowling ball and the marble. Obviously, the bowling ball is bigger than the marble, right? But compared to the earth, the bowling ball and the marble are the same thing. The earth is that big. The earth treats those two objects as the same thing. The bowling ball and the marble. And I mean, and we can go even larger. We can say it could be a boulder or something, right? They're all gonna fall. Compared to Earth, they're nothing. So they're gonna fall to the Earth at the same rate, no matter what. And so that's what happens, right? And so if you pay attention to the cartoon, so the lady has the piece of paper in her, that's her left hand, right? So she has the piece of paper and she has the ball in the right hand, and she on the left hand side, which is the first image A, right? She drops the ball in the paper at the same time, and the ball falls, crashing towards the earth, and the paper kind of just floats, right? But if she balls the paper up, and the paper starts to take on the shape and the dimensions of the ball, then what happens? Then they fall to the earth at the same rate. Okay? So the moral or the lesson of this story is that, right? Is that the only thing that stops or the only thing that changes how things fall towards the earth is air resistance, right? And so with air resistance there, right, some things, say for instance, like a feather, like if you drop a feather, then the feather is going to take forever to hit the ground. Okay, that's because the air is able to move through the feather with relatively ease, and so it kind of floats, or kind of floats through. It kind of moves through the air like a fluid, right? Because the air is a fluid for all intents and purposes. Okay, but the bowling ball sort of cuts through. It cuts through and goes straight. It cuts through the air and goes straight to the earth. Okay, so That's the difference between the two images, A and B. All right. And so this is the Leaning Tower of something, Pisa. I guess that's the name of it. But the lesson here is that you see that we can track how far. Now, see, this is motion in one dimension, but the direction is what? Vertical. So we're dropping something, some object off of the tower, and we're calculating how far it travels after so much time has elapsed, right? And we're going to do an experiment like this, okay? And we're going to create one of these plots, okay? And I also should point out that this number is the number that we will be using for the acceleration due to gravity. So you're going to be using this number quite a bit. 9.80 times 9.80 meters per second squared. Okay, so commit that to memory. All right, and graphical analysis. So we've sort of done some of this already when we looked at the two different the horizontal lines, but let's look at it here, right? This is more of a line which is it's not completely horizontal and it's not vertical either, right? So it has a slope, right? The velocity is the slope of the x and t curve, right? So x is position. So I'm changing position on the y-axis, right? And I'm changing time. My time is getting longer on the x-axis as I move to the right, right? And so if I take the slope of that line, I can calculate my velocity. So that goes back to v equals what? Delta x, which is here. Delta x over what? Delta t. Okay? So, 11 meters per second, right? So delta x is 11, delta t is 1. So I put that 11 over 1, and I say that object is moving at 11 meters per second. That's how fast that object is moving, right? So I was able to determine that from the graph, right? Which had nothing to do, not directly with velocity. It was position and time, right? But they are all related, okay? But you don't know that if you don't know kinematics. All right, and I think that's about it, folks. Well, let's go over the summary. And kinematics is a description of how objects move with respect to a reference frame, right? Displacement is a change in position of an object. So if I start from the beginning line, I don't know what you call that, from the start line, right? I start from there and I end there, then my displacement is 0. I didn't change. I started there and I ended there, but I know I traveled a distance around the track. Okay. Average speed is the distance traveled divided by the time it took. Right? That's what speed is, right? Understand the difference. Speed is distance. The distance you went around the track divided by the time it took. Velocity, I already told you it was 0. Why? Because you started and ended up in the same spot, which made your displacement 0. 0 divided by t is 0. All right. And instantaneous velocity is limit, blah, blah, blah. And I think that's it, right? All right, so that's it for this one. That's it. Thanks.